All right, everybody, class recording has started. So, over the past couple days, we have been discussing mostly these two pictures down at the bottom, right? We talked about Bohr's model, we talked about Schrodinger's model, okay? Both of them are trying to do what for us? What part of the atom specifically? They mostly deal with electrons, location of electrons, right? What did we learn? How did we transition from Bohr into Schrodinger? What did Bohr say about those location of electrons? Go ahead, Joe. They're in certain spots, right? He called them shells, right? Those are the rings that show up on this picture, right? But Schrodinger, right, realizes what? They could be anywhere, but there's certain locations that are more probable than others, right? So why don't we start on the first page of the outline, not your picture, on the actual first page of your outline, and let's fill in some things here about the background of our quantum mechanical model. Okay? So first, based on the work of Heisenberg and Schrodinger, okay, first, Heisenberg. Do you remember what Heisenberg did for us? Some stuff, good, yes, hold on. Okay. Heisenberg came up with or realized the whole Usain Bolt thing that we talked about in class. Do you remember the Usain Bolt? The uncertainty principle, right? That we can't know the speed and location of electrons. We can know one, but not the other. We can't know both, okay? So based on the work of Heisenberg and Schrodinger, we get to the conclusion that we will never know the exact locations of electrons around the nucleus. But Schrodinger looks at, like we said, old data, right? Data that represents where electrons were in the past and comes up with these areas of high electron density. There are certain places around the nucleus where electrons have been more often in the past. And if they've been there more often in the past, what can we do? Say that they might be there in the future. We can predict that that will be a likely place for them in the future. And what do we call those areas of high probability? Orbitals. Okay? They're not orbits like Bohr said. They're orbitals, right? Okay? We think they're going to be there, but nah, we're not really sure. Okay?
Pretty much like the first question in the bullseye lab.
Yeah, pretty much. Yep. Yeah, that's actually, and then also question number 4 talks about, can you make a hypothesis, right? A hypothesis is what? An educated guess. Can you make an educated guess about where an electron is going to be based off of where they've been in the past? Yes. Does your educated guess have to be right? No, but we can make an educated guess. All right, so just to review, going back to this picture, right? Our big picture that represents all the stuff we drew over the past couple days. Each one of these spaces that we drew is an orbital. Okay? This is an orbital, and 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 this is an orbital, etc., etc., etc. These are all orbitals. Okay? But what we'll find as we go along here is that just because these orbitals exist, there are certain ones. Two things. One, we have to have a way to distinguish each orbital from all the other orbitals. Okay? And 2, we'll find this out a little bit more next week, just because these are orbitals, areas of high probability, some have higher probability than others. And we'll talk about that more next week. So how do we distinguish all these orbitals from each other? We use, well, on our drawing we use colors, but we assign a set of numbers to each orbital. And we call those numbers the quantum numbers. No, there's a pattern. There's a pattern. Each orbital on that picture that we drew and all the other orbitals that we didn't draw, because there's lots more that keep going with that picture, all of those orbitals have a unique combination of quantum numbers that distinguishes it from all the other orbitals. We will start working on assigning those quantum numbers today, and what do they tell us, and why do certain orbitals get certain combinations of numbers and such. But think of it like your address. Let's say your address is 123 Main Street, Westlake, Ohio. That address is unique to your house. It describes a location that is different from all the other locations, all the other houses in the country. Are there other houses that have a house number of 123? Yes. Are there other houses that are on Main Street? Yes. Are there other houses in Westlake? Yes. But there's only one house that is 123 Main Street, Westlake, Ohio. And that's what the quantum numbers tell us. All of those things that we drew in the picture are orbitals, but each one of them is unique, and we have to have a way to distinguish it from all the other orbitals. Okay? Good with that? So that's where we're headed here over the rest of today, and then into, we'll probably pick this up on Monday. Let's go back to the beginning. Okay? Orbital number 1, orbital number 2, 3, 4, 5, 6, 7, 8, 9. Okay? First, when we change, this is a dumb question. On the picture, I had you color coordinate certain orbitals. Hopefully you picked up on that meant something. Right? The first way that we distinguish these orbitals from each other is by what we call the principal quantum number. Notice principal is P-A-L, right? Not P-L-E. We use the lowercase letter n to represent the principal quantum number. The principal quantum number, like it says, is the main energy level where the electron is found. So we start with principal quantum number 1, then we go up to 2, then we go up to 3. If it's the main energy level, what does it describe for us? What tells us about the energy that electrons have? Distance from the nucleus. So the principal quantum number is going to roughly describe how far away these orbitals are from the nucleus. Orbitals that have lower principal quantum numbers are going to be closer to the nucleus. Orbitals that have higher principal quantum numbers are going to be farther away from the nucleus. Good? Okay. Here's our first orbital that we drew. What do you think its principal quantum number is going to be? Very low. 1. So, for this orbital, my magic pen.
Oh, it's right here.
Was it behind the Kleenex? Oh, it's right here. All right. I should really put like a bell on it or something. All right. So for this orbital right here, this is the first orbital closest to the nucleus. So it has a very low principal quantum number. In fact, its principal quantum number is 1. So for this orbital, n is equal to 1. I know that that's not the greatest color in the world, but I'm trying to keep it consistent with the color. So like I said, when I'm going to keep, when I write quantum numbers that describe certain orbitals, I'm going to use the same color that we drew them in. All right, so, and oh, if you wanted to, I kind of, like, we made the little detail drawings, okay? You can use those little detail drawings maybe on this part, too, to put those quantum numbers. Yes, Norm?
There's 3, right?
Say again?
There's 3. Right?
Actually, there should be 4.
Yeah,
No. Remember, this is not the nucleus. This is the first orbital. It's small, but it's the first one. Okay, good. What was the next orbital that we drew? Red sphere. Okay? Notice the color changed. On our drawing, every time the color changes, that's a new principal quantum number. So in this case, this orbital has a principal quantum number n equal to 2. Okay, but the next orbitals that we drew, 1, 2, 3, right? What color are they? They're still red. So this one on the x-axis right here, its principal quantum number is n equals 2 because it's still red. This one on the y-axis, its principal quantum number is 2. It's still red. This orbital, the one that's on the z-axis, its principal quantum number is also 2. Notice, remember when we were drawing, when we drew like the double teardrops, right? We said that these are the double teardrop orbitals. I told you to draw them just a little bit further than the sphere. Remember that? Hopefully, yes. Okay. That implies that they are a little bit farther away from the nucleus, but they're still, the sphere and the double teardrops are still pretty close to each other. Okay? But then after we did this, what was the next one we drew? Blue sphere. Color change. That represents a new principal quantum number. So the principal quantum number for this orbital is going to be n equals 3. Okay? And same with these, right? And then also same with this one. The double petal flower, or the 4-petaled flower. It's blue, so its principal quantum number is also going to be 3. Okay? Nora, go ahead.
How do you know which numbers are the same since they don't have
Like in real life?
Yeah.
Okay. In real life, it depends basically on how close they are to the nucleus or how far away they are from the nucleus.
Yeah, but like the ones that are like on top of each other with the petals.
Okay. Notice that for the petals, right, especially here, these are all blue, meaning that they're all kind of on top of each other. Does that make sense? They're all approximately the same distance from the nucleus. So they all have pretty similar energies. Not the same, similar. Because, remember we talked about that this whole drawing is trying to balance how close an electron can get to the nucleus while still staying away from all the other electrons. And once we get out here to principal quantum number 3, we've got more area for them to spread out, so we have little variations in energy even though they're kind of close. Does that help? Okay. All right. So here there are 4 orbitals on this picture. Sorry. There are 4 red orbitals on this picture. All of them have a principal quantum number equal to 2, but they are clearly different from one another. Yes? Okay. So the next way that we start distinguishing orbitals from each other is by their shape. If you go to the second page, I'm going to skip a bunch of stuff on the bottom of the first page. We'll come back to it. If you come to the second page, you will see a chart down at the bottom that looks like this. Huh? What? Okay. Well, let's make it less confusing. Say again? Just because that's a different book that I got it out of, you know. So yeah, books decide which ones they're going to call X, Y, and Z. Although we'll see in a second that how you do that really doesn't matter. All right. So there are 4 types of orbitals. We categorize them by their general shape. The first orbital that we drew when we changed colors was always what shape? It's always spherical. The first orbital of a color was always a sphere. We call spherical orbitals s orbitals. So any orbital that is spherical is an s orbital. Okay? The next one that we added on were the double teardrops, or the figure 8s. Right? Those we refer to as p orbitals. The figure 8s, regardless of whether it's a figure 8 on the x-axis or a figure 8 on the y-axis, or a figure 8 on the z-axis, all of those are p orbitals. The next shape we introduced was the four-petaled flower. Four-petaled flowers we refer to as d orbitals. Okay? Regardless of what color they are, if they're the four-petal flower, they're d orbitals. And then at the end of class yesterday, right, I told you that there was another shape that we weren't going to try and draw. It was like an 8-petaled flower, right? We refer to those 8-petaled flowers as f orbitals, but you're not going to have to draw those.
So it's like
Seven complex shapes.
Seven. Okay. So
n equals 2s.
okay. So now here, we know that n equals 1 here, and we know that n equals 2 there. But what's similar about these two orbitals? They're both spheres. They have the same shape. So the next quantum number tells us about the shape. And we refer to that quantum number as the angular momentum quantum number. Okay? We use the lowercase letter L. I will try to always make it as like a cursive L so it doesn't look like a 1. All right? So we use the lowercase letter L to represent the shape of the orbital. We assign the angular momentum quantum number based on the shape. So any spherical orbital has, these are L's, that's an L right there, even though it's not the same cursive L as this one up here, right? These are L's, okay? Any s orbital, spherical orbital, gets an L value equal to 0. Any p orbital, any figure 8 shaped orbital, or double teardrop, is going to get an L value equal to 1. Any four-petaled flower, any d orbital, is going to get an L value equal to 2. Okay? So if we go back to our drawing, we know that this orbital has a principal quantum number, n equal to 1. It also has an angular momentum quantum number. The angular momentum quantum number tells us the shape. What shape is this orbital? Spherical. It's an s orbital. So that means its angular momentum quantum number is going to be 0. Any s orbital is going to have an angular momentum quantum number equal to 0. Okay? Good there? Here, we said this is a new principal quantum number. It's a little bit farther out from the nucleus than the first one. But what shape is this orbital? It's spherical. And all spherical orbitals get a principal quantum number equal to 0. This one, what shape is it? Spherical. It's an s orbital. It's an s orbital in the third energy level. But because it's an s orbital, L is equal to 0. Okay? Say again? Yeah, there's another big one. Well, I'll save that one for later. Do we understand that so far? All right. Now let's head back here. Okay? These are 3 separate orbitals. They are all in the second energy level. That's why they have a principal quantum number equal to 2. What shape are they? They're a teardrop, double teardrop. And we said double teardrops are what kind of orbitals? Those are p orbitals. All p orbitals, regardless of what level they're in, get an L value equal to 1. Okay? If we go to this picture, okay? If we started naming quantum numbers for this one here on the x-axis, what would its n value or its principal quantum number be? 3. It's blue. What shape is it? Double teardrop, right? It's a p orbital. All p orbitals get L values not equal to 0. All values equal to 1. Okay? Good so far. All right. What's the problem here? Okay. What are we seeing about all 3 of these orbitals so far?
Oh,
They all have the same address so far, but they're not the same orbital. So we get
They're on different axes.
right. They're on different axes, right? These are all houses that look exactly the same and are on the same street, but they're not the same house, right? So we got to come up with a way to distinguish these from each other. Magnetic quantum number. So if you go to the top of page 3, okay, it's like, wow, he's so smart. Told you you're going to have to write 4 numbers. Well, that was the very first thing we wrote down, right? Quantum numbers. How many quantum numbers are there? 4. All right. So the magnetic quantum number, we use the lowercase letter m to represent the magnetic quantum number. So it says, indicates which orbital the electron is in within each sublevel. Sublevel is the shape. There are 3 p orbitals in the second sublevel. Which of the 3 p orbitals are we talking about? That's what the magnetic quantum number does for us. We know there's a p orbital on the x-axis, and a p orbital on the y-axis, and a p orbital on the z-axis. Which one's which? That's what we got to tell us here. Okay? All these, this here, this last bullet point, possible values go from, that is negative L to positive L. Sorry, second period had a problem with that too. Yeah. So here, where this statement right here, okay, possible values go from negative L to positive L, not negative 1 to positive 1. Okay?
So it's negative L, 0, and L.
Good. Well, now,
This paper
hold on.
Then they have
So hold. Sorry. I'll show you that in a second. Okay, hold on a second. Okay. All right. So just write that negative L to positive L. Okay. Good with that so far? Okay. All right. Let's take it back to the drawing.
So these are
Sorry?
all these, they're called the quantum numbers.
These are collectively, these are the quantum numbers. Okay. Here is an s orbital in the first energy level. Because it's an s orbital, its L value is 0. If we use that little thing that we just talked about, m values run from negative L to positive L. What's negative L in this case? Negative 0. What's positive L? Positive 0. Is there anything that's different about negative 0 and positive 0? No. No, it's not. Right? So, what is this saying? If there's an s orbital, how many s orbitals can there be? Just 1. How many spheres did we draw of each color? Only 1. Why? Because there's only 1 s orbital. So anytime you have an s orbital, L is equal to 0, but m is also equal to 0. Do we have to distinguish between multiple s orbitals? Nope, there's only 1 s orbital in each energy level. So we don't have to talk about, well, which s orbital are we talking about? There's only 1 in each level. Okay? So then, here, okay, what shape is this one?
Sphere.
It's a sphere. L is equal to 0, but if L is equal to 0, M is equal to 0. How many red spheres are there on the whole picture?
1.
1. Okay. Good there so far? This is where it starts getting a little tricky. Okay.
That was already 15.
All right. M values, all of these are going to have an M value. In the outline, it says M values run from negative L to positive L. What's L for a p orbital? 1. So that means M can be negative L, negative 1, to positive L, which is positive 1. But what do you have to go through to get from negative 1 to positive 1? Well, on a number line, to go from negative 1 to positive 1, you have to go through what?
0.
You have to go through 0. So if L is equal to 1, M can be negative 1, or 0, or positive 1. How many options is that? 3. How many p orbitals are there? 3. Coincidence?
No.
All right. So if you go back to your outline, right, it says M is equal to negative 1 for the x-axis p orbital, M is equal to 0 for the y-axis p orbital, and M is equal to 1 for the z-axis p orbital. So if we go back to this picture, which axis is this p orbital on? Usually that's the x-axis, but you want to call y, that's cool, right? So that means here, okay,
Negative 1 or
that's negative 1.
we just put x and y?
No. I mean, like, well, if I'm not going to give you quantum numbers that way, right? You can, like, what I'm trying to show you is, like, this is the x-axis, right? Okay. All right, this is on the y-axis, right? This p orbital is on the y-axis. So its M value is going to be 0. And this one here has to be equal to what? Positive 1. You should put positive, yes. That's cool. We will do a lot more practice with this, so it's easy to do. Okay?
Does that mean all the other ones on the other levels are the same?
Okay, so now let's go here. Okay? All right, so let's go here.
Sorry.
All right, here's p orbitals again. These p orbitals are all in the third energy level.
Wait, what's the sphere?
What is a sphere, Edie?
M is equal to 3.
What do we call? Yeah. Oh, yeah. Sorry. Here. Okay. Okay. So L is equal to 0 because all spheres are L equals 0, right? And that means for this one, how many blue spheres are there? Just 1. So if L is equal to 0, M is equal to 0 as well. Okay. How many p orbitals in this picture? 3. They're all in the third energy level, so they all at n equals 3. What are their L values? Because what shape are they? They're all p orbitals. They're all double teardrops. Any double teardrop, no matter where it is, has an L value equal to 1. But we've run into that same problem again. We have 3 different orbitals that have the same 2 quantum numbers so far. That's where M comes in. L is 1. There are possible possible M values run from negative L to positive L. Negative 1, 0, positive 1. 3 possibilities for how many orbitals? For 3 orbitals. Okay. Joe asked, is the x-axis always -1? Okay. So, okay. All right. Here's my XYZ axis, right? X is the solid wood one. Y is the purple tape. Z is the white one. Yes? Yeah. Ready? Okay. Did I change the atom at all? Just depends how you look at it. So, the moral of the story, and this is not meant to confuse you, it's just the way that it is. Does the x-axis one always have to be -1? Not necessarily. But what does it have to be?
Equal to L.
No.
Negative L.
What does it have to be compared to the y-axis one? It has to be,
The same as
all right, no.
the opposite.
It has to be different.
Oh.
Okay? The first two, hold on, we're almost there. The first two numbers for all of these orbitals are exactly the same. So the third number's got to be different. If I call this -1, what can I call the y-axis one? I could call it 0 or +1 as long as it's different. But if I call this one -1 and this one +1, what does the z-axis one have to be? It's got to be 0 because it's got to be different than the other two. Okay? Hey everybody. I know that you guys might not totally be there yet, but I want you to know, as a teacher, watching you guys do this and having you guys answer questions, I feel that you are farther along that path than other classes have been because you have the whole picture and now we're just labeling parts of the picture instead of trying to build the picture while we're labeling it. So just so you know, I'm happy with where you are right now. We will continue this on Monday. Okay?